going to go over the syllabus today. I was like, I probably should. Haven't been to work in 20 days. That's a long time. Okay, what we're going to do today, first let me talk about lab. So for lab this week, we're going to do last week's lab and this week's lab. This week, both are very short. So, I mean, we still should finish early. But my Tuesday group will do it first. And if I need to make any adjustments, I will. But I'll send that out in the email. So you're doing lab 13 and 14 this week. Today, there's a few problems. I need to rework. One, I need to work for the first time. Well, there's two I need to work for the first time. Then I'll go over any homework problems y'all want me to go over. Wednesday, bring me questions from chapter 9, 10, or 11, whatever. It can be from the book, from practice I've posted, whatever. I'm leaving the class up to you. So if you don't bring questions, we'll start chapter, I think it's 13. Yeah, 13. And then test Friday. Okay. So we can talk more about the format of the test on Wednesday as well. All right. What I need to rework is example 11.5. All right. I messed up. It was the Clausius-Clapeyron equation. So I worked this one, but I lost my negative. So I just figured we'd rework it. So there are a lot of equations on this exam. So for this, I'll give you this equation. I think it's the hardest to remember, the easiest to mess up. With your P's and your T's. All right, so pressure can be in any unit we want. Our delta H of vaporization has to match the units of our R. Remember, this R is in joule per mole times Kelvin, not liter times atmosphere, blah, blah, blah. So the value's a little different. I'll also give you all your constants on your test. So I'll give you this R value. You just have to know when and where to use it. So I always convert my delta H of vaporization to joules, because I just have to move my decimal to make that number large. Okay, so I just moved my decimal 3 places to the right. And then I need both of my temperatures always in Kelvin. So we'll do the normal boiling point as our T1 and our P1. So T1, 64.6 plus 273. What is P1 then? It's the normal boiling point. 1 atmosphere. Okay, now I need to do the same thing with your second temperature. So we're looking for P2. T2 is 12 degrees Celsius plus 273. All right, now let's plug all those into our equation. P2 is what we're looking for. P1 is just 1 atmosphere. Remember, you can't do anything here because you can't do any simplification because of this P2 is unknown. Then negative is part of the equation, so negative 35,200 joule per mole over 8.314 joule mole Kelvin. And 1 over T2, which is 285, minus 1 over T1, 337.6. All right, so let's simplify the right side. First thing I'm going to do is I'm going to divide my delta H of vaporization by R. Cancels. We have Kelvin in the bottom of the bottom, so it moves to the top. All right, now I'm going to do my temperature term. I'm going to do 1 divided by 285 minus 1 divided by 337.6. If you don't get what I get, it means you didn't use enough parentheses. All right, so that's what I got for my temperature term. All right, now I multiply those two. I multiply these two together. Don't lose my negative this time. That's where I messed up. That's where I messed up in the lecture video. Units of Kelvin can't. All right, so to get P2 by itself, I've got to get rid of this ln. To get rid of the ln, I take the inverse ln. So the inverse is just that E raised to this power. We all found the ln on your calculator. It's under log if you have one of these. Right there, so I just do second ln, it gives me my E. So E raised to the negative 213 power then to get P2 by itself, I just multiply both sides by 1 atmosphere so that it becomes .0988 atmospheres.
I entered into my calculator. I got 0.099.
That's okay. Any other questions? I don't think I messed up this time. Yes,
So why use 4 instead of?
that's fine. You can, yeah, so you can use torr, millimeters of mercury, kilopascals, whatever you want, as long as when I go to convert it, it gives me the same atmospheres or whatever. I'll try to be more specific on your test and tell you what units I want to do. Another vapor pressure. Let's see. All right, let's do, instead of doing the next one that's in your notes, I'm going to do number 63 out of your textbook. No, I'm not. I'm going to do number 64 out of your textbook because it's looking for a temperature. right, so again, we're given our heat of vaporization. Let's go ahead, convert that to joules. So move your decimal, make it a column. There's that. And then I have a normal boiling point of 80.1. So we'll do that as T1. Right. So since it's normal boiling point and the other pressure I'm given is torr, let's make P1 a pressure in torr. So what would it be? Yeah, 760. Okay, then we don't know T2. We do know P2 is 445 torr. Okay, now let's plug everything in. And then a P2, 445 over 760 torr equals negative delta H of vaporization over my R over T2, I don't know, minus 1 over T1, which is 353.1. All right, this time I can go ahead and handle the left side of the equation. I'm not doing the inverse this time, I'm doing the LN. So I push LN, gives me a parentheses, 445 divided by 760, close parentheses, enter. And I get negative 0.535. Now I'm going to go ahead and divide delta H by R. Right, there's several things or several ways we could go from here. I think the easiest is going to be to divide both sides by negative 3.69497 Kelvin. That cancels. While I'm here, I'm gonna go ahead and do 1 divided by 3. 3.1. Good up to there. I'm gonna add the 0.00283 Kelvin or inverse Kelvin to both sides. So moving this over here. Now I have 1 over T2, but that's not what I want. I want T2. So to get T2 by itself or to get T2, so basically what I'm doing is I'm multiplying both sides by T2, then dividing by this to get T2 by itself. Or you just cross multiply. T2 becomes top, this becomes bottom, and it's 1 over that, which is what it is. So then when I plug that in, I get 336 Kelvin. Any questions there? Okay, then what we need to do now is, oh, I'm sorry.
How come you put the 445 over the 760 instead of putting LNP2 over
P1.
just the 445?
Okay, so I just made my T1 and my P1 my normal boiling point. Then I made the one that I'm looking for, T2 and P2.
Okay.
So anytime it says normal boiling point is blah, 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 that means at a pressure of 1 atmosphere. So since we already had this in torr, I just said, okay, well, let's just use torr.
Okay.
You could have converted this 445 to atmosphere. You would have gotten the same thing.
Okay. And if I did convert it to atmosphere, I would still put the 760.
You put 1 atmosphere
Okay.
here, and then whatever this was. Anything else? All right, job to do number 70. Oh no, y'all do odd. Alright. The next one I am going to work, you have to do 69. So we'll do 70 first, and then if we have time, we'll come back to 69. 70 is a heating curve of a liquid. And it was it was like those 5 slides I kind of skipped over. No, let's do 69 first. This one's going backwards. Let's see how this one different. 10 grams of ice. All right, so really this is the only question or the only part of the question. It says how much heat in kilojoules is required to warm 10 grams of ice at -10 degrees to steam at 110 degrees Celsius. They also give you the heat capacity of ice and steam, but that's not all you need. You need a lot more than that. So on your test, the easiest way to know that you're not using the QMCAT equation is you're going to be given a bunch of stuff. You're going to be given 5 ice, liquid, steam, vapor, confusion. So I gave us ice. They did not give you all this in your textbook. They assumed that you would go look it up. But on your test, I'll give you this 5 pieces of information. All right, so this is what a heating curve of any substance is going to look like. I'm about to make it specific to water. All right, so I told you in the PowerPoint that when you are heating a liquid that, in our case, was at -10 degrees, what I'm starting at is -10 degrees Celsius. If I heat it, the temperature is going to increase until I get to its melting point, which for water is 0 degrees Celsius. So all the heat that I'm supplying goes to raise the temperature to 0 degrees Celsius. Okay, that's the straight line. When I get to 0 degrees Celsius, I flatline because that is the melting point of water. So then all the heat goes to make my ice a liquid. So I'm not actually increasing my temperature. I'm going through a phase change. So this is a phase change. Once I have converted all of my ice to liquid, I keep supplying heat. Once it's all been converted, then my temperature will begin to rise again until I get to 100 degrees Celsius, which is what water boils at. So then I flatline again. So this is another phase change. Once I've converted all my liquid water to steam, then the heat that I'm still supplying will go to raise the temperature. In this case, we want to stop the temperature at 110 degrees Celsius. Okay, so there's 5 different pieces that you have to work. I'm going to number them. 1, 2, 3, 4, and 5. 1, 3, and 5, you use the Q equals MCAT equation. For 2 and 4, that's your phase change. You use Q equals N, which is the number of moles, times delta H of that phase change. So down here, it would be the delta H of fusion. Here, it would be the delta H of vaporization. Fusion. Vape. So you have to do 5 different problems, then you have to add them all up. And that will give you the amount of heat required to warm 10 grams of ice. So let's start. For the first one, we're going to need mass. so we don't have to convert it to moles, but we are gonna need moles when we get to 2 and 4. Let's just go ahead and go up here. Convert 10 grams of water to moles, so we'll have it ready when we need it. And divided by 18.2. Now we're ready to go. All right, so part 1. Q equals MCAT. I always draw this diagram out so that I know my delta T's for each step. You don't have to, but then the specific heat that you're going to use. Think about what state of matter you're in this region of the graph. From -10 to 0, I'm in a solid or ice. So I'm going to use ice as specific heat. So 10 grams. 209 joules. And then my delta T, my final temperature would be what? Final temperature would be 0, because that's where I'm going to end. Minus initial, which was -10 degrees. So those two negatives cancel. So I'm going to say 10 times 209 times 10 gives me my heat of step 1. Or none. 209 joules. And the problem says how much heat in kilojoules. So we're going to want all 5 of these answers in kilojoules. So let's go ahead and convert it. 1,000 joules in 1 kilojoule. So 0.209 kilojoules. Right, step 2. You're just saying number of moles times your delta H of that process. So we went ahead and we found our moles, 0.555 moles. The delta H here that I'll use is fusion because it's going from solid to a liquid. The moles cancel, I'll be left with units of just kilojoules. Okay, so that's the second part. Now I'm going to the third part, which again, I'm going back to my QMCAT equation. I'll be using a different specific heat because now I'm in the liquid phase and a different delta T. So plug in 10 grams, specific heat of liquid water, and then your delta T. My final temperature would be 100 right here. My initial would be 0. So I'm gonna do that. I get 4,180 joules. Again, let's go ahead and convert it to kilojoules. So I'm dividing by 1,000. Okay, now I got 4 and 5 left. 4, I'm back to a phase change. So it's just N times my delta H. This time, vaporizing, I'm going from a liquid to a gas. So I'm gonna use the 40.7. As you might guess, there will not be more than one of these on your test because it will take you forever. Twenty-two 22.6 kilojoules per fourth. And the last one, went back to my QMCAT equation. This time I'm going to use the steam specific heat and different delta T. So 10 grams, 201 is my specific heat, and then my delta T is 110 minus 100. So that's going to be 201. And there's piece number 5. Now you have to add all 5 of these up to get your final answer. So all the numbers I have boxed, you add up and you should get 30.5 kilojoules. Is the total amount of heat required to warm that ice. All right, don't forget lab 13 and 14. I'll email you those to remind you. See you on Wednesday.